Jad Al, Property Project Coordinator at OPA. OPA would like to welcome you to this webinar under the title of Reservoir Fluid Sampling. The agenda for today's session is: first, my colleague Engineer Isam will be delivering a presentation about our November and December training courses. Then, Engineer Mohammed Ameen will conduct a technical session. I would like to introduce you to Engineer Mohammed. Engineer Mohammed is a senior reservoir engineer at General Petroleum Company, GPC, Egypt. He has more than 5 years experience into asset evaluation, reservoir characterization, and simulation. He participated in and recently managed many successful field development plans in green and brown field within offshore GOS area. Engineer Mohammed has a correlation that holds his name in field reservoir fluid flow modeling. Engineer Mohammed holds a bachelor and master degree in petroleum engineering from Suez University in Egypt. He has many publications into several journals and conferences like MPM, IGRTE, and PNC. Now, Engineer Isam will conduct the presentation. Engineer Isam, the stage is yours.
Thank you, Jad, for the introduction. This is me, Assam Helmi. I'm a business developer at OPA, Online Petroleum Academy, and one of the OPA Egypt team. In this presentation on the title of OPA November and December courses plan, before I go through my presentation, I'd like to give you a short note about the courses that we conducted in the last several months. In July 2020, we conducted 2 courses, which are Prosper and Online and Oil Field Manager. And in August and September, we delivered 2 courses, which are Sapphire Well Test Analysis and the Gaps Surface Network Modeling. In October 2020, we conducted 2 courses, which are MBAL for reservoir modeling and BIPSIM for nodal analysis. OPA is offering a great discount on these courses, up to 45% discount from the original courses of these courses. So you can enjoy your discount. The main target of this presentation is to give you a note about our courses for November and December. We have 2 courses, which are TechLog Software and Petroleum Economics. The TechLog Software is from 28th of November to the 3rd of December. And the Petroleum Economics course is from the 5th of December till the 10th of December. Each course is 6 days, including an off day between these days for working on additional assignments. 15 intensive hours, 3 hours per day for petroleum engineers, geologists, and economists, delivered by high experience instructors. One of them is plus 15 years experience. What will you learn from the TechLog software training course? You will be able to be familiar with the database setup, quality control, data and data loading from the DLIS or the LAS files, depth matching between the different wells, curves placing between different log runs, lithology identification from well logs, shale volume calculations, cutoffs and summations, construction of formation evaluation models, combining formation evaluation models. And if you would like to know more about the TechLog, please go visit our page on Facebook. You will find the proposal for the TechLog software. You will find the detailed information. And regarding what you will learn from the petroleum economics course, you will be able to know the common evaluation tools, the economics analysis components, time value, economic indicators, advanced topics. And also, if you are interested to know more about the details of this course, go visit the proposal of this course. You will find the detailed information. Again, you can enjoy your discount. You can invite your friends from all over the world and enjoy a big discount on this, up to $60 instead of $100 for a group of 5 persons or members. Now you can go for your association in your country based on where you are based. We have partners in India, which are EduCave and Geotized. In Lebanon, we have six partners actually: the AABG LU student chapter, the SPEPAU student chapter, SPELEU student chapter, SPELU Romania student chapter, NDU Petroleum Engineering Society, Engineering Society at Phoenicia University, and in Creek we have our partner Technical University of Crete SPE student chapter. So go and ask these associations if you belong to one of them, and you will find a great discount that we are sharing with this association, and enjoy your discount again. Uh, some people and a lot of people asked us about these software courses, and we promise that in the near future we are planning to conduct reservoir modeling using Eclipse and Petrel. For the petrochemicals, we are planning to conduct Aspen HISES software training course, Emirate for production logging tools, PLT, BVT SIM for the BVT analysis, and Schlumberger FracCAD for designing your hydraulic fracturing. If you are joining us now, so you are lucky, you can get the gift voucher to one of our courses. We will give two vouchers, one for the TechLog software training course and the other for the petroleum economics training course. You, by joining us today, have saved your place in the pool, but you have to do the other conditions that we mentioned in our social media platforms. So if after finishing this webinar, go and visit the page and make sure that you apply all the conditions so that you can get the offer. Uh, the last thing that I want to mention to you is being an ambassador in OBA is simple. You have to take only one course with us. After that, you are one of our ambassadors. What will you get by being an ambassador in OBA? You will enjoy huge discounts on our courses. Uh, the last thing, if you would like to apply for the petroleum economics or the TechLog software courses, you can scan this barcode. I will let this slide for a moment. In the meanwhile, my colleague Jad will send in the chat the link for applying for these courses. Thank you, and I'd like to welcome Engineer Mohammed to the stage. Thank you, Engineer Mohammed, for joining us, and back to you, Jad, to start the webinar.
Thank you, Isam. So please all take a moment to check the link that I have shared with you on the chat and register to our upcoming softwares and courses, please. Now, Engineer Mohammed Ameen, the stage is yours, and welcome again.
Thank you, Jad. Thank you, Asom. And thank you all OBE team in Egypt and all over the world. This session is about the reservoir fluids sampling and the classification. Our agenda for today, we will learn about reservoir fluids classification and its importance into reservoir engineering applications. And finally, we will get a brief notes about reservoir fluid sampling. For reservoir fluid classification, we learn it from our books that we have about four types for oil reservoirs, and also we have four types for gas reservoir. But actually, in the industry, we have about only five types of reservoir fluids. We have the black oil reservoir, black oil fluid that engages the ordinary black oil and the low shrinkage crude oil. Also, we have the volatile oil fluid reservoir fluid that includes the near critical crude oil and the volatile crude oil. For gas reservoirs, we have three types. We have dry gas reservoirs, we have wet gas reservoirs, and gas condensate. The gas condensate reservoirs, including the retrograde gas condensate reservoirs and near critical gas condensate. And we will learn how to differentiate between these types of reservoir fluids. We have three methods to identify our reservoir fluid. First, if we have the composition of our reservoir fluid, we can construct the phase diagram or the BT diagram for this fluid and locate the reservoir pressure and temperature on the phase plot. And upon the location of reservoir pressure and temperature, we can know the reservoir fluid type. The second method is to monitor our production performance, and the production data can tell us more information and more actual sense for our reservoir fluid. The third method is when we have the composition, we can locate this composition on McCain-Ternary diagram, and and so we can know our reservoir fluid type. For oil reservoirs, as we mentioned, we have about four types of oil reservoirs fluids. We have the ordinary, we have the low shrinkage, near critical, and volatile crude oil. But actually, we have only two in the industry. We deal with only two types of oil reservoir: the black oil and the volatile oil. For low shrinkage oil reservoir, for production performance, we have initial GOR about less 200 standard cubic feet per standard barrel, oil barrel, and the API will be less than 35. For the phase diagram, here we have this line representing the reservoir conditions, temperature, and pressure, and the point G is representing the separator conditions. So we have the temperature is less than the critical point. So we have an oil reservoir. And also the pressure and temperature point is far away from the critical point. So it is likely to be black oil reservoir for the journey of the oil from the reservoir through the well and to the surface. It loses a lot. It loses some gas. For the low shrinkage oil, it has low gas to be lost to the system. So low shrinkage occurs for this type of reservoir flow. The ordinary black oil has more gas than the low shrinkage oil reservoir. So its GOR between 200 and 700 standard cubic feet per standard oil barrel, and the API ranges from about 15 to 40. The location of reservoir pressure and temperature is nearer than the location for the low shrinkage black oil reservoir. For the volatile crude oil, its initial GOR from about 2000 to 3200 standard cubic feet, and the API between 45 and 55. We can notice that the reservoir pressure and the temperature is becomes near to the critical point, and the volatile crude oil has more gas, more gas, more dissolved gas that be lost on the surface or separated by the production facilities. For the near critical crude oil, we can see that the reservoir pressure and temperature becomes very very near to the critical point represented by the point C on the phase diagram. So we can see that when the pressure uh, being about 50 10 to 50 psi below the bubble point, its volume shrinkage from 100% to about 55%. So it loses a lot of volume by pressure decline. Also, the production performance, the initial GOR is higher than 3,000 to about 3,000 and a half or 3,200. standard cubic feet per standard oil barrel. And for its composition, the C7 plus percent is ranging from about 12.5 to about 20 mole percent. For ethane to hexane, the composition will contain about 35% mole percent, and the remainder will be methane. The volatility characteristic trend for volatile oil reservoir, we can note that the API is increasing by the time. The reason for that is that at the initial time, the gas produced is from the oil phase into the reservoir, but by more production from our reservoir, the most oil is coming from the associated condensate with the separated gas. So the API will increase as a result of increasing the condensate ratio for the oil production. Summary, oil reservoirs, we have this plot for the various oil reservoir fluids. We have the low shrinkage represented by A, the curve of A, and B representing the ordinary black oil, and C for high shrinkage, and D for near critical. So the near critical oil reservoir has the greatest shrinkage between all oil reservoirs. And uh, for also for phase plot, we can notice that the black oil is far from the critical point, and the volatile oil is near to the critical point. To differentiate between the black and the volatile oil into the industry, or and actually the difference between black oil and volatile oil, it depends on the RV. RV is representing the amount of oil associated with the separated gas. So the separated gas by the production facilities, it if it has about from 1 to 10 standard oil barrel per million standard cubic feet, so it is black oil reservoir. If the RV for the separated gas is ranging from about 10 to 300 standard barrel per million standard cubic feet. So we have volatile oil. So the big constraint for volatility, or the difference between the black and the volatile oil reservoir, is for the RV. The RV is the amount of oil associated with the gas separated. For gas reservoir, we know that we have four types for gas reservoir: dry and wet, and the condensate reservoir representing retrograde gas condensate and the near gas condensate. For the dry gas reservoir, the composition will still in the gaseous state into the reservoir conditions, the reservoir pressure and temperature, and also as a surface, it will still into the gaseous state. So no liquid is formed from the dry gas reservoirs. The GOR for dry gas reservoir is more than 100,000 standard cubic feet per standard oil barrel. So it is very, very low GOR. For wet gas, the difference between wet gas and the dry gas is that the wet gas remains into the gaseous state into the reservoir pressure and temperature, and also when the reservoir pressure declines, it also will remain into the gaseous state. But when this gas is coming to the surface, some oil are precipitating from the gaseous state and form it into or form it as a liquid into the separator conditions. So this is the difference between dry gas and wet gas reservoir. The GOR for wet gas reservoir is ranging from 60 to 100,000 standard cubic feet per standard oil barrel. And also the API for the separated oil above 60 degrees. For gas condensate reservoirs, the temperature is located between the critical point and the crecondensatherm. The crecondensatherm is the point as the last oil droplet will become as into the gaseous state. So the retrograde gas condensate in the reservoir life at the initially with production, some of this gas is condensated condensed as oil phase into the reservoir until it reaches to the maximum point or the maximum point of liquid drop out. Then because the attraction forces between the heavy component molecules will become more than the attraction between the heavy molecules and the light molecules. So this heavy molecules is condensed as oil phase into the reservoir. But when the more depletion into the reservoir pressure occurs, these heavy components follow the normal vaporization process when the pressure declines. So the liquid drop out is returning back and decline. The GOR for retrograde gas condensate is ranging from about 8,000 to 70,000 standard cubic feet per standard oil barrel. The API above about 50 degrees. For near critical gas condensate, the reservoir temperature is very, very near to the critical temperature for this composition. And also, the temperature is located between the critical point and the condenser. A rapid liquid dropout occurs with the pressure declines, as we see on the liquid dropout chart. To differentiate between gas condensate and the volatile oil reservoir, for composition, the volatile oil contains more than 12.5 mole percent of C7 plus, and the gas condensate is condensate less than that number. Also, the gas condensate GOR is greater than 3,000 and half standard cubic feet per standard barrel. So we use the first and the second method for differentiating between oil and gas reservoirs using the composition and locating the reservoir pressure and temperature on the phase plot, and also recognizing the production performance or the initial production from the reservoir. The third method is to use the McCain ternary diagram. The ternary diagram of McCain, we have 3 points or 3 corners for the ternary diagram. The first corner is for methane and nitrogen. The second corner for C7 plus, and third corner for methane to hexane and CO2. So by locating and intersecting these points of composition, the intersecting point, we have 4 segments for gas condensate, volatile, ordinary, and low shrinkage and dry gas systems. When the intersecting point is located into these segments, we can identify the reservoir fluid type. Also, again, for production performance, the black oil has the GOR is increasing when the reservoir pressures decline below the bubble point. Then the GOR declines again due to depletion. Also, the EPI declines gently with time of production. For volatile oil, the GOR is increasing when the pressure declined below the bubble point, and the significant differentiating between the black oil and the volatile is for EBI. The EBI for volatile oil reservoirs is increasing with time. For gas reservoirs and retrograde gas reservoirs, the GOR increase by time and also the EBI. For wet gas, the GOR is constant because the wet gas is still and will still into gaseous state into the reservoir conditions. And also the EBI is constant. For dry gas, no liquid dropout occurs. We have three properties also to differentiate as a summary between the oil and the gas reservoir, that the initial GOR and the EBI and C7 plus mole person into the composition of reservoir composition, the black oil and volatile retrograde and wet gas, dry gas, and the GOR by using the GOR, excluding any well issues like gas cooling or any well problems, we can identify our reservoir fluid. We have some examples. We have a well that producing initially with an EBI about 54, and the initial GOR about 23,000 standard cubic feet. So initially, as the GOR is above 3,000 and a half standard cubic feet, so we can suggest that it is a condensate, gas condensate reservoir. Second example for a field that has a GOR 2000, so it is an oil reservoir. And also the GOR is about 2000. It is very high to be black oil, so I suggest to be volatile oil. Also the EBI increased from was increasing from 51 to 63, so it is a significant property for volatility. So we have a volatile oil reservoir. We can notice also in the composition below that the C7 plus mole person is about 14.91, so it is higher than 12.5%, so it can a volatile oil reservoir. The third example, the yield or the RV representing the oil associated with the separated gas. The initial yield is about 125, so it is very high, and it can be gas condensate reservoir. This example for the GOR versus production time, we have that the average GOR is about 300, so it is black oil reservoir. We have also the GOR versus production time. We have the initial GOR about 30,000, so it is on the border between the wet gas reservoir and the condensate gas reservoir. So it can be gas condensate reservoir, and also it can be treated as wet gas reservoir. Also, we can note that the GORs increased after some point, so we can expect that this point is the pressure declined below the dew point for this reservoir. For this example, we have the GOR versus also the time. The initial GOR is about 90,000, so it is very high. Also, the EBI is increasing with the time, that indicates gas condensate reservoir. So it can also it can be gas condensate reservoir or wet gas reservoir. For this example, the GOR starts from very low number and then increasing for very high number. We depend on the initial GOR value. So it can be black oil, and this trending of increasing the gas production, it can be from gas cooling phenomena. So we know about our reservoir fluid types, and we can now classify our reservoir based on the composition and the production performance. So uh, at this point, we want to know what is the importance for the reservoir fluid identification. The first importance for the reservoir fluid identification is using the suitable method for PVT modeling and material balance simulation. For example, for black oil and dry gas, we can use the black oil correlations like Biggs and Brill and these correlations for black oil, and this called black oil model. For volatile oil and wet gas reservoirs, the separated gas is associated with some oil that's separated from this gas. So we use correlations for the RV, or the yield that representing the amount of associated oil with the gas production, and this method is called the modified black oil model. For gas condensate and very volatile oil reservoirs, we use the equation of state or the compositional model. This is an example for using or for wrong using of the conventional material balance for volatile oil reservoir. So the prediction for this reservoir, when we use the conventional material balance, it gave us a very high GOR, but when we use the modified black oil model or the volatile oil material balance, we achieved a very good match for the actual performance, and also it matched the separator gas oil reservoir. Also, when we know the reservoir, our reservoir fluid, we can forecast or expect the future productivity problems. Like for gas condensate reservoir, for gas condensate reservoir, in some cases, a condensate ring is formed around the well bore. So this condensate ring is lowering the productivity of the gas well. So when we have gas condensate reservoir, we can expect that we will have some productivity problems in the wells that can be solved by using the gas recycling and the other method for stimulation. Also, identification the reservoir fluid can lead us into our economic feasibility studies for the reservoir fluid, such as that we know that the crude oil is classified as light, medium, and heavy according to the API density. So when we have an API ranges from about 40 to 45, we can expect that our oil will have a very high price. But when we have the API above 45, so the 45 API oil is less than or less valuable than the oil that having gravity from 40 to 45, because the hydrocarbon chains becomes very short, and this short hydrocarbon chains want won't lead to a high amount of energy like that generated using the oil having API gravity 40 to 45. So we ended our journey with the reservoir fluid classification, and we will go through the sampling techniques for the reservoir fluids. Our objective into reservoir fluid sampling process is to have a representative sample for our reservoir, because we will use this small sample from our reservoir to simulate or to mimic the depletion and the geometric behavior for the reservoir fluid into our reservoir. Our techniques into sample, we have two broad categories for the sampling: bottom hole sampling and surface recombination sampling. This diagram can lead us into our sampling process to use either the bottom hole sampling or surface sampling. For oil reservoir, for black oil reservoir, when we know that the reservoir pressure is above the bubble point, we use the bottom hole sampling. When we have the reservoir pressure at the bubble point or below the bubble point, we can use the surface recombination sampling technique. For volatile oil, the volatile oil, we use a surface recombination that is used also for all types of gas reservoirs. For bottom hole sampling, we have three techniques. We can use the formation tester if we have an open interval. This tool is lowered onto the wire line or electric line, and something like a needle. This needle is inserted into the open hole interval and sucks some of our reservoir fluid. And when we know that the fluids going through our tool is representing the reservoir fluid, we can sample this fluid into some chambers inserted into this tool. Also, if we have a cased hole conditions, we can use the wireline sample catchers. The wireline sample catcher is a tool that is lowered into a wireline or a slick line. Uh, this tool is catch some of the fluids into the wellbore and return it to the surface, and we can check its validity on the surface. If we are doing a wellness step, is to use when the needle of the entity or the RFT is inserted into the open hole interval, and starting pumping out the fluids from the reservoir. In the beginning, the mud filtrate is being sucked from the open hole interval, and then the reservoir fluid begin to go through the tube. So, the mud invasion fluids stage, the resistivity is very low. But when the oil insert or started to being going through the tool, the resistivity becomes higher, and so we can begin the sampling process. Also, for the MGT or RFT tools, we have the optical fluid analyzer. The optical fluid analyzer is using the optical properties for the various fluids. So, when we start the pumping out fluids from the reservoir, so it uses the optical properties for water and oil and gas to interpret it as a column indicating or interpretation for the fluids being pumped from the reservoir at the beginning, as we see from at one. So it is a mud filtrate, so it is labeled as blue. Then the oil fraction increased until all the sampled fluids are representing the reservoir fluid. So at this stage, we can start the sampling process. For MDT, for steps for sampling, first, we can choose the good fishes that have high mobility that can help us into our sampling process. Then we can measure the pressure and the mobility. If we have a valid pressure reading and a high mobility, that's typically higher than zero point 0.5, we can bump out and analyze the fluids that are being pumped through the MDT tool using the resistivity reading and also the optical fluid analyzer. If we have represented fluid to our reservoir, we can start sampling the process. But a caution is needed that we should avoid sampling below the saturation pressure, because if we sample the reservoir fluids below the saturation pressure, so we will have a multi-phase flow into the tool. So the multi-phase flow will lead to not representing sample for our reservoir. Also, we can take more than one sample, one as main sample that will be sent to the lab for experiments, and the other sample will be as a backup sample. The sampling time is depending on the cleaning and the amount of mud invasion into the reservoir, and also the formation mobility. If the mobility is very high, so the sampling time will be very short. The other method is the surface recombination system. The recombination system or the surface recombination is to collect gas sample from the gas out of the gas out of the separator, and also collect an oil sample from the separator. Then recombine the some amount of gas to some amount of oil according to the production GOR. But before this sampling occurs, we should condition our well to have a representative fluid sample. So the first step is to reduce the production flow rate by 30% or 50% of its production rate. If the GOR remain constant, we can take the sample. If the GOR is not constant, we can reduce the flow rate again on some stage. If the GOR stabilized, we can take the sample. If the GOR is not stabilized, so we can again reduce the production flow rate and see if the GOR is stabilized. We can reduce also the flow rate to minimize the drawdown from the reservoir. Finally, this sheet is for recombination samples taken from a separator. A condensate, three condensate samples and three gas samples. Uh, the sample will be labeled for the temperature of sampling and also the pressure for the reservoir for the separator, and the volume of sample and the bottle number, sample number. Thanks, and any questions?
Okay, thank you, Engineer Muhammad. Please, if anyone have any question, don't hesitate to ask in the question and answer part, please. We have a question from Iman asking which type of gas reservoir is the best, retrograde gas or wet or dry?
Is the best for what? This This question is very general because يعني what is the best for what?
Okay, Iman, if you can please ask your question again to be more clarified. If you can please. Some people are asking if they can get the slides. This webinar will be on our YouTube channel, so you can find it whenever you want. Of course, after we upload it, and also don't forget to like and subscribe to our YouTube channel. We have a question. Why the API is increasing rapidly in volatile?
Yes, because in the beginning of production, the greater portion or the greater fraction of the oil is coming from the oil phase. But at the late time of production, the greater fraction of oil production is coming from the condensate that is separated from the gas that is being separated from the oil phase. So we know that the condensate has a high EPI, so the final EPI for the oil production will being higher and higher by the production.
Okay, please, if anyone have another question, please just mention it. Okay, we have a question from Dr. Rami, who is asking, what is the most common used method for testing fluids?
The common methods for testing fluids.
Yes.
Okay, if you are talking about the experiments that is being done in the lab for oil reservoirs, for oil reservoirs, we have the compositional analysis. The compositional analysis is being done for all reservoir fluids. For oil reservoirs, the routine experiments are the CCE or the constant mass expansion and the differential liberation and also the separator test that is being done to select or to determine the optimum separation for the production facility. For wet gas reservoirs and also the gas condensate reservoir, the CVD is being done instead of the differential liberation for oil reservoirs. So the CVD is for constant volume depletion.
Okay. Does reservoir enhancement depend on whether it is dry gas or wet gas?
Can you repeat the question?
Yes. Does reservoir enhancement depend on whether it is dry gas reservoir or wet gas reservoir?
Reservoir enhancement? I don't
It's
understand the question.
okay. Please, if you can also clarify your question. There's another question. When do we use CGR?
The CGR is for condensate gas ratio for the yield or the RV. All these terms is for the associated oil with the separated gas for the gas production. What is the amount of oil that is associated with the gas production, and it is measured into a standard oil barrel per million standard cubic feet.
Okay. We have a question. What type of gas reservoir can get more economic benefits? And which reservoir is the best economically?
Okay, it varies from field to field, and what is the recovery from each field. and what is the facilities available in each field. A lot of parameters included into the feasibility studies to answer this question that is very variable between the oil and gas fields. So a lot of variables should be estimated before answering this question.
Okay, thank you. So before ending our webinar, Sam will send now on the chat a feedback form. So please fill this form to help us always be better and better. Okay, we will take some more questions before ending our session today. We have a question from Salman who is asking in GOR, how do we separate harmful gases?
Harmful gases, harmful gases that like CO2 and H2S. Uh, it is this question is concerned by the facility design, like sweetening process and the production facilities design. A lot of production facilities equipment can be used to separate the CO2 and H2S gases from the stream of gas production.